Hi everyone, welcome back to the channel. In our last video, we delved into the world of Pytorch optimizers and we discussed an algorithm named as AdaGrad algorithm. The algorithm aimed to tweak the learning rate at each step, but there is a catch. AdaGrad algorithm did hit a roadblock where the learning rate kept on decreasing over the period of time. Let's take a closer look at the learning rate adjustment step of the AdaGrad algorithm and understand it mathematically. So the adjusted learning rate gamma is equal to gamma, which is the actual learning rate, divided by 1 plus t minus 1 into eta. So eta over here is the learning rate decay and t is the number of iterations we are taking. And by one iteration we mean one complete forward and backward pass, whether it is happening individually or whether it is happening in a batch. Usually, the learning rate is a value between 0 and 1, and more likely it is a very small value like 0.001 in ideal scenario or 0.01 as we considered in our example. There might be a possibility that the denominator is so huge than the numerator that the adjusted learning rate kind of tends to 0. Now, how exactly it is going to affect the algorithm? Now, if we recall that the parameter updation step, that is the value of theta t plus 1, was equal to theta t minus gamma cap into a gradient value, which was gt divided by square root of st plus epsilon. Now, if gamma cap is kind of tending to 0, theta t plus 1 is going to be pretty much similar to theta t only, which will mean that after a particular set of iterations, we are not going to get an updated value of theta, and hence there might be a good possibility that the minimal value of the function f which we considered, f theta, which we considered, hasn't even reached yet. So this algorithm, which we will be studying today, which is the AdaDelta algorithm, overcomes all these drawbacks, and we will be following this paper, AdaDelta and Adaptive Learning Rate Method. And I will be providing the link to this paper in the description. And also, as we did in the previous video, we will make an attempt to understand the torch implementation of this algorithm with a small numerical example, which we will first solve on pen and paper and then write a code of that problem. But before understanding the entire algorithm, let's talk a bit about an important concept which is being talked about in this paper, which is called as learning rate annealing. This is what we are going to talk about. And once we talk about it, we will be very much confident on what exactly is being implemented in this algorithm. Learning rate annealing simply means learning rate adjustment. Here we can do a learning rate adjustment in two ways. We can either speed up the learning rate when suitable, which will mean that in the initial stages of the iteration steps, we can tend to make the model learn faster and we can have a very high learning rate, or we can speed up the learning rate. And when the learning has stabilized a bit, then we kind of reduce it. And the second way is we slow down the learning rate when we are near the local minima. The algorithm, AdaDelta algorithm, focuses on the second approach. And how it focuses on the second approach of learning rate annealing, it will be a bit clear when we will try to understand the entire algorithm. So this is the AdaDelta implementation as taken from the paper. Now if you go through the paper and then look at the torch implementation of this algorithm, which is over here, you might feel that there is a gap between how the algorithm is implemented in the paper and how it is exactly being implemented in Pytorch. Actually, the Pytorch documentation is implementing the exact same algorithm, just there are some notational inconsistencies while moving from the research paper to code. We will discuss that in detail. And the main aim of this video is to bridge the gap between what is there in the paper versus what is there in mentioned in the documentation of Pytorch, which we will be eventually using. So let's try to understand it and elaborate wherever it is possible. The first step is we have a function f of this form f theta. We have this function, and our objective is to minimize the value of f and find a corresponding theta which minimizes it. And the function f is such that the first order gradient exists, gradient of f. Now this gt, the value gt is equal to gradient of f at theta t minus 1. Like depending on the number of iteration, the value of gradient will be calculated, and the value of gradient at the previously calculated value of theta is what gt is. So now if I come inside the loop after doing all the initialization step, the first step is to compute the gradient of the function which we have. The second step is to perform the calculation for the accumulated gradient, but we need to first understand what this accumulated gradient means. Let's try to expand this equation manually and try to visualize what we are getting. So now if I expand the equation, so this is the equation which we are having, and we tend to expand it, and I start with the value of t as equal to 1. I substitute t is equal to 1. I get rho times expected value of g naught square plus 1 minus rho times, and rho is actually a decay parameter. This is a hyperparameter only, g1 square. Now g1 is the gradient value and g1 square is the squared gradients which we are considering. So gt is exactly what I have mentioned over here. This is what is gt, and g1 is the gradient at iteration 1. g1 square is the squared gradient at iteration number 1. Now we proceed further. On proceeding further, we replace t with 2 over here, and hence we get expected value of g2 square is rho times expected value of g1 square plus 1 minus rho g2 square. Now since expected value of g1 square is already being attained over here, which is this is the expected value of g1 square, we straight away substitute it. So instead of expected value of g1 square, we substituted the value as this, and g2 square remains as it is. Now if you can see the implication, or if we try to understand what exactly is happening at this stage, this is kind of a concept which is similar to exponential smoothing. Those who have understood time series forecasting or who have studied time series forecasting, they will be able to relate it, that we put in more preference to the latest values and lesser preference to the previous value, or just a value before. Likewise, we are giving more weightage to g2 square over here, and we are giving kind of a lesser weightage to g1 square. Now we move a step ahead and calculate expected value of g3 square. We replace t with 3 over here. We get rho times expected value of g2 square, and this is exactly what we have calculated over here, and 1 minus rho times g3 square. Just we do the substitution and we get this value. Here again, if we observe this equation which we have attained, what we are doing, we are giving more preference to the current value squares, like g3 square is being given more preference, and as we move back in time, we are giving lesser and lesser weightage to the older gradients. And gradient is nothing but the information which needs to be updated. This is very much clear from the previous video, that whenever we have an information which we need to update in the parameter, we consider the gradients only. So what we are saying is we give more weightage to the current information at that particular step. Let's suppose we are at step 3. We are going to give more weightage to the gradient at step 3 and lesser weightage to the gradients at step 1 and 2. And we can do it for expected value of g4 as well. And again, we are going to view that the more preference is given to the squared gradients at the fourth iteration, and lesser preference is given to the gradients of the previous iteration. And as we move ahead, the gradient of the first iteration is going to get the least preference. The latest gradients are going to get more preference, with the highest preference being given to the current gradient square. So now we can make a substitution over here. We substitute the expected value of gt square with vt. So we do this. Now on doing this, we have this formula which kind of becomes vt is equal to rho of vt minus rho of gt square. This is what we are getting over here. Now if I see the Pytorch implementation, just a minute. Yeah, if we see the Pytorch implementation of this algorithm, we can see that this term Vt is equal to Vt minus 1 rho plus Gt square 1 minus rho, which is being written over here. This is exactly what we have attained over here. This is exactly what we have attained till now. Now we look into this algorithm again, the algorithm from the paper. We see that we are able to consider the accumulate gradient step in a proper way. Now we will move a step ahead and go to the fifth step, which is the compute update. But before doing that, we will consider another recurrence formula which we are seeing over here and try to understand what exactly it is doing. So this is the recurrence formula which we just saw. So delta xt square will mean something. I will come to it, but just for understanding purpose, consider this as a recurrence formula only. And let's try to expand it in the same way as we did for the previous step. We substitute t with 1 over here, and then we expand it, so we get the expected value of del x1 square as this. Now we put the value of t as 2 only, and then we expand it, and we are almost getting the same sort of progression for expected value of del xt square as we were getting for expected value of gt square. Now we make a substitution that we assume the expected value of del xt square as ut, and we rewrite the entire equation and we get something like this. Now if we look back at the algorithmic implementation, this step ut is equal to ut minus 1 rho plus del xt square 1 minus rho, the second last step, this is what we have attained. So in the paper it is written in expected value of delta xt form, but in the Pytorch implementation the same expected value of delta xt is replaced with ut, while the expected value of gt is replaced with vt. So till now we are able to understand that we are able to make some consistent replacements, and we are able to draw a bit of analogy between how things are written in the paper as well as how things are there in the Pytorch implementation. So the two recurrence formula which we were using in step 4 and 6, we were able to expand it and we were able to find out the corresponding implementation in Pytorch as well. Now if I consider the fifth step, which I kind of skipped, and try to expand it, there is actually a definition of RMS which is mentioned in the paper, which is this. RMS of GT is square root of expected value of GT square plus epsilon. This is from the paper only. And RMS of delta XT minus 1 square is this. Now we substitute expected value of GT square with VT because we have made this substitution, and this expected value of delta xt minus 1 is replaced with ut minus 1. We must remember it's t minus 1, so we do the like to like replacement only. Now we look into the algorithm which is there in the paper and see what delta xt is. Delta xt is negative of RMS, the ratio of the two RMS value multiplied by GT. Let's try to expand it now. So this is how it is written in the paper, and based on the substitutions which we have just made a step ago, which is this and this, square root of Vt plus epsilon ut minus 1 plus epsilon, we put it over there, and this is the delta xt step which we are getting. And finally, the parameter update step from the paper only is coming out to with this. Theta t is equal to theta t minus 1 plus gamma times delta xt. Now there is a small deviation which we can see. In the implementation, you won't be seeing a negative sign over here. Now since the negative sign isn't there, in the final updation step it is minus of gamma times delta xt. But in the paper, since the negative sign is already there, in the final updation step they have made it plus, and the implementation is exactly the same, and that's what I have told over here. So this is from the Pytorch documentation. If I follow the documentation, delta xt is calculated like this, and this is going to be the updation step, while if you follow the paper, this is the delta xt and the corresponding update step is this. Now if we see the PyTorch implementation from the paper, and based on the derivations which we have done till now, we can easily observe that this Vt which is mentioned in the paper is nothing but expected value of gt square, and this ut is nothing but expected value of delta xt square. That's it. So it's exactly the same algorithm which is being mentioned over there, just that for notational convenience they replace vt and ut, they replace the expectations with these two terms, and just the negative sign of the updation is used because the delta xt is having a positive sign. The rest of the implementation is exactly the same as it was there in the paper. So till now we were able to understand the algorithm, at least in abstract sense. We will spend a little bit more time to understand how the learning rate annealing is happening over here in the algorithm. Now the concept of learning rate annealing had been spoken in the paper, and it is also mentioned that the AdaDelta algorithm follows a learning rate annealing where the learning rate decays when it reaches the minimum. Now this is how the things might look. GT is the gradient which we are having. And if we use a little bit of our high school mathematics, if we have to find the minima of a function f, what we do, we take the first order derivative and equate to 0. Now, whenever the gradients or the GT are kind of tending to 0, this will mean that the learning rate needs to be reduced because the algorithm is reaching more and more towards the minima. And how exactly we are capturing the GT? We are capturing it with the VT over here, and we are also capturing it with delta xt. So if I look at the definition of delta xt, it considers both um, a scaled weighted value of gt in terms of ut and vt. So if gt is tending to 0, then it will mean that delta xt, which is some term into gt, it will tend to 0 as well. So whenever that thing happens, we will be able to kind of scale the learning rate in a way that it is kind of minimal, or we will be able to decay the learning rate in a way that it is minimal whenever it is reaching the minima or the local minima corresponding to the function f. So now we are going to understand the concept or get a little bit of hold about how the iteration works with a small numerical example. We consider the same function as we did in the previous video, x square plus 5x minus 8, and this is the functional form in theta. Like I replaced x with theta so as to make it a bit more coherent with how it is implemented in torch. And this is the first order gradient of f theta, which is 2 theta plus 5, and these are the initial values we start with. We start with a learning rate gamma as 0.01. We start with the decay as rho. This is the value of rho as 0.9. Weight decay, it is just consistent with how it was there in AdaGrad as well. The same weight decay is being implemented here in this paper as well, which I considered as 0.005. I start with the initial value of theta as 3, and as per the paper both V0 and U0 will be 0, and we considered the value of epsilon as this. Now just to reiterate, this is how the algorithm is looking like. Yeah, this is how the algorithm is supposed to look like. We have gamma, we have the value of rho, we have the value of lambda, we have V0 and U0 set to 0. So basically these terms we know we have initialized these terms, and also we have considered the value of theta naught as 3. Now we will proceed further to perform the first iteration of this algorithm. So I will keep this implementation handy so that it is easy to follow. The first step is to do this step, gradient of f theta t minus 1. So g1 will be gradient of f theta naught, and twice of 2 theta naught plus 5. I substitute the value of theta naught as 3, and this is the g1 which I am getting. And since lambda is not 0, we consider the value of lambda as 0.005. We do the weight upgradation step, which I have mentioned over here. And now we proceed with the calculation of Vt on this step. Since we have gone through the paper, we don't have to explicitly call out Vt as expected value of Gt square every time. The notation is for understanding only. So we will just put the value of t as 1 and the rest of the values as it is. And on solving, we are getting the value of V1 as this. We put the value of rho as 0.9 as we have initialized. V0 was initialized to 0. 1 minus rho is 1 minus 0.9. And G1. Now this is the updated value of G1 which we should be taking, not 11. So we take the updated value of G1 and square it, and this is the value of V1 I am getting. Now we can calculate delta xt as well over here, as it is mentioned in the algorithmic flow. So delta xt, this step we are going to do, it takes into account ut minus 1 and vt. And in our case, if t is 1, ut minus 1 will be u0 and vt will be v1. We have this formula. We know that u0 is 0 as it is initialized, like we have to initialize u0 with 0 only. And on the top of it, v1 we have just calculated, g1 we already know, g1 is 11.015. We are just going to substitute the values and let's see what we get. On substituting, and also the value of epsilon was given. On substituting, we get the value of delta x1 as this. Now we proceed further and then we see what the next step is. So the next step is the calculation of ut, which we write the formula for, and then we substitute t as equal to 1 and replace it with the values which we are having. So as of now we are able to get the value of delta x1 as well. Now we update the value of u1 and then we get u1 as this, a very small value which is kind of near to 0, but still it's a value which we have to calculate. Eventually we do the parameter update step, which is going to be the final step, and this is how we do. We put the value of t as 1, so theta 1 is theta naught minus gamma times delta x1. Delta x1 we have already calculated, and the theta 1 comes out to be 2.99. That's it. Now since we have done iteration 1, we can proceed with iteration 2 as well. It's not going to be that tough, as we have already done one iteration. We will follow the same steps. We will calculate the gt first, where t is equal to 2. Again we are going to solve for v2. We replace t with 2 and keep on solving it, and we keep on solving and we get the value of delta x2, we get the value of u2, and eventually we get the value of theta 2 as 2.994. It is a very slow progression which we are observing, that the value of theta 1 initially was 2.997 if I am not wrong. Yeah, 2.997 was the value of theta 1. It reduced a bit to 2.9994. Now if I continue at this pace, it's going to take a very long time if I even calculate with pen and paper. Let's try to experiment with this entire algorithm on Pytorch. So now we are going to do the Pytorch implementation of this algorithm. A lot of steps are going to be exactly the same from the previous video, so I'm not going to do the hands-on over here. I urge you to visit the GitHub repository link as mentioned in the description for this code, so that you can run it from your end. And we are just going to import torch over here, which we will be needing. we declare the function fx over here, which is x square plus 5x minus 8, and all the parameters needed for the AdaDelta implementation are mentioned. For instance, we consider the learning rate as 0.01. Let's bring up the pen and paper implementation and use the same parameters, yeah, over here. So we considered the learning rate as 0.01, and the decay we considered as 0. Just hold on a second, 0.9. So we mentioned that. So learning rate is 0.01, the decay as 0.9, the row is mentioned as decay over here, and the weight decay was 0.005, and I guess that's what we took, yes. And we started, and epsilon is 0.00001 as we have mentioned, and x is 3. We started with the initial value of 3 only, theta naught is equal to 3. U naught and V naught are actually not needed to be initialized, those are initialized by default. So whatever needed to be initialized, we do that. We run this segment of code and then we create the optimizer object over here, and it is torch.optim.AdaDelta. As simple as that. We consider the parameter over which the backward propagation is needed, and all the other um, hyperparameters of this optimizer are mentioned over here, like learning rate, weight decay, rho, and epsilon. Everything is mentioned. Now we do this step for 1000 iteration, and there is a small change over here. What we do, we are just going to calculate the norm of the gradient as well. So we run this piece of code and let's try to see what we are observing in about 1000 iteration. So we see that in first step we are getting 2.99968, much similar to what we got. We got 2.4 times 9 7 in our first iteration. So this was the first iteration which I did, and I got 2.4 times 9 7. So approximately the same value I am getting in the first iteration itself, and the gradient value is also 11, which we have got. Just that an adjustment was done, so gradient value of 11 exactly we got in the first iteration. Let me check. Yeah, this is the gradient value of 11. So it clearly matches with how we were getting the results. Later on the gradient adjustment happens and then the iteration goes. And then we proceed ahead with the further iteration steps. And we see that the gradient value is decreasing. It is decreasing, but not up to that level it should be. Like in 1000 iterations, and let's see what is the final value I am getting over here. So it's norm with brackets. Yeah. So the final value which we are getting is this. So the value of f is 15.17, x is 2.92, and the gradient value is 10.84. Let's try to increase the number of iterations now. We say that we can run it for around 5000 iterations and everything should remain the same, and we run the code and let's see what we are getting. So in 5000 iteration we were able to get, and the final value of f we are able to get to 9. Like it started at the gradient value of 10.99, the functional value started with 15 or 1615. It reduced, but it is not reducing to that minimal value. There is still scope of improvement as well. Now we can increase the number of iteration, but we can also keep tuning the learning rate as well. Now we keep the learning rate as 0.09. We increased a bit, like we have increased the learning rate. We create the optimizer, and let's say I do it for around 3000 iterations, uh, and then we run it. Let's see what we are supposed to get now. So now we are seeing that the values are decreasing aggressively. Now the gradient value is still not equal to 0, or nearby close to 0, but we can see that at 2900 iteration the value of f has reduced. The value of x is also kind of pretty less, and the gradient value is 5.69. So now we need to reduce it even further. Now what we can do, now we can increase the number of iteration. Let's say I do it for around 5000 iterations. and keep everything consistent, and we run it for 5000 iterations, I think. Yeah, it's kind of reaching the minima where it should be reaching. So as of now, we were able to get the gradient value as 1.51. The value of x is minus 1.74 and the minimum value is minus 30. Let's take a bit of more steps, like let's consider like 7000 steps, run the algorithm again, and let's see how we are getting the results. Now slowly and gradually you will see that it's tending to 0. Yes, it's kind of tending to 0 with the value of x as minus 2.49. Let's go back to our pen and paper implementation and try to see what exactly should be the minimal value. So we have the value of fx as x square plus 5x minus 8. Now the first thing which we need to do is calculate the gradient of fx, which we were able to rightfully calculate as 2x plus 5. Now to calculate the minima, we equate the gradient of fx to 0, and on doing so we get the value of x as 2.5. And if I put the value of x as 2.5 over here, like this will imply that f of 2.5, if I calculate it, it's somewhere close to 14. And now if I do the double derivative of fx, like f double dash x, it is going to be 2, which is strictly greater than 0, which will mean that this value of 2.5 is the local minima. Now let's see the results which we have obtained over here. We have obtained the result of minus 2.49. So first of all, it is going to be minus only. It is because if gradient of fx is 0, this 5 will come to the RHS with a negative sign. So, and the value of f 2.5 is minus 14 approximately. So on doing so, we are approximately equal to or near to the minimal value, which is minus 2.5, and the minimal value of the function is minus 14.24, which we are getting over here. And the gradient value is kind of close to 0. Now, if it had been 0, it would be completely 2.5, but since it is not 0, it is kind of hovering around the same area. Let's increase the number of iterations even further. Like from 7000, I increase the number of iterations to 9000. And I run the code again. And let's see what final values which we are getting right now. So we get like kind of the same value. I think the value stabilized a bit. Yeah, the value stabilized a bit over here, and it didn't reduce further. We can kind of use something like a learning rate scheduler over here, which we will be discussing much later in the videos or in the subsequent classes. So on from what we are getting is, we are kind of getting the minimal value using the numerical approximation methods of optimizers, and the minimal value is 2.49, and the minimal value of the function is coming out to be minus 14.25, which is kind of similar to what we are getting over here if we have to solve it using pen and paper. So yeah, that concludes the video. And to recap, we started with the one of the drawbacks of AdaGrad algorithm, and we were able to read the paper and understand that the AdaDelta algorithm uses the learning rate annealing, where it slows down the learning rate whenever it approaches the local minima. We were able to understand the algorithm and kind of correlate it with the implementation in Pytorch as well. While doing so, we were able to understand the concept of weighted expectations, which means that giving more weightages to the current values and less weightage to the old values. And over here, the values mean the gradients, which will mean that we give more preference to the current information and less preference to the older information. And we were able to understand the concept of how the second way of annealing is working over here, that as and when the gradient is tending to 0, the learning rate is kind of decaying, in a way that the algorithm kind of converges to the optimal value or the minima. We considered a small numerical example to get kind of a pen and paper understanding of how the algorithm works. We did it for around 2 iterations on pen and paper, and after that we considered our code in Colab. We did the same implementation as we had done in the previous video for the same function, just that we updated the parameters of AdaDelta optimizer, and we did it for like around 9,000 iterations. We did a little bit of parameter tuning though. We started with a learning rate of 0.01 and realized it's very less to get the convergence done. So we increased the learning rate, which is kind of a way of tuning the parameters only. And then we ran it for like around 9,000 iterations, and we concluded that we are getting a value which is kind of very close to the actual minimal value of the algorithm if we had to calculate with pen and paper. So that's it from this video. In the subsequent videos, we are going to discuss more about the different types of optimizers which are available. We will be solving one concrete example end to end on a realistic problem with different types of optimizers once we have finished our understanding of all the optimizers in Pytorch as well as the learning rate schedulers. In the next video, we are going to discuss about the Adam optimizer, which is a widely used optimizer in most of the deep learning problems. Thanks for your time.